Good afternoon. So in this lesson, we're going to introduce the topic of vector spaces, and we will move on to applications and the computational aspects of them rather quickly. So this isn't the scope of this lesson and the class itself. This is, remember, a 1-hour credit class. It's not to go too deep into the theory of vector spaces, but to just have the sufficient insight and the computational skills to actually move on to the applications in other courses as soon as possible. In this particular case, applications in the context of differential equations. So I'm going to talk about some motivation. You can write this down. I'll talk about on this motivation that I wrote here already on the slide. And we're going to focus primarily on the main definition and properties and some intuitive understanding of those properties. We're not going to go, for example, too deep in the theory, in the sense of checking those properties for weird types of vector spaces. So primarily the vector spaces you're going to handle actually in this class are those coming out from matrices or the vector functions given by vector spaces given by functions. Again, primarily in the context of differential equations. Many of you actually have seen vectors in the context of physics. So roughly speaking, these are algebraic structures that can describe visually complex systems. This is kind of a vague descriptions, but in particular situations where the quantity has a direction and magnitude, you have seen this already, those of you who took calculus 3, right? In which the vector, which is represented geometrically by a quantity which encapsulates these two components, some magnitude given by a positive number and a direction of some sort, like a velocity, for instance. Or when linearity properties are prevalent, and this is more in the context of differential equations. What do I mean by linearity properties? Well, basically, each time you can actually distribute some sort of operations to a sum, a linear combination. So the classical example in calculus is differentiation or integration of linear combinations, like, if I have some constant times f of x plus some constant times g of x, the differentiation, has that linear property in the sense that the constant doesn't do anything. You can pull it out of the derivative, and the derivative itself distributes itself over the summation. So that's an example of a linearity property. Vector spaces are inherently linear, as you will see. So, by the way, from now on, you can already call a vector, for example, a column matrix. So even before I give you a definition, we can interchangeably use the term column matrix with a vector, because if we identify, let's say in the 2x2 case, if you identify a column matrix or a row matrix for that matter, because depending on the context, you can write these vectors by row or by column. You can identify this column matrix by a point in the plane. And if you want to associate a direction given by this, you can connect the point to the origin and then, declare that the direction given by this vector is the arrow that points from the origin to the point itself. So again, if you took calculus 3, you have done this before in the context of calculus 3 topics. So now the important thing before we move on to the definition is to realize that vectors don't have to be matrices. They can be really pretty much any mathematical object as long as it follows the formal definition of a vector space. So let's move on to the formal definition. A vector space is a collection of objects mathematical object denoted sorry, it's kind of a messy here, denoted by u bar, v bar, x bar, y bar, etc. So by convention, we put a bar on the top of these variables to distinguish them from real numbers or numbers in general. Now, in the most of the books, they will distinguish them by using bold letters rather than the bar on the top. But obviously, when we take handwritten notes, it's not going to be easy to make that distinction. So the convention is to put the bar on the top. Sometimes you have an arrow if you have to really be more specific in terms of the direction from one point to another. So it's a collection of objects denoted by this convention together with scalars, which in the context of vector spaces, at least the ones that we deal with them, are just real numbers. Now, they call scalars for two reasons. The most important one is that in the context of vectors, real numbers in those operations involving vectors really have one of the main roles is to manipulate the magnitude of those vectors. And so basically to scaling up or down, right? But also, as I said, in its most abstract setting, these scalars don't exactly have to be real numbers, although you're not going to encounter this type of situation. So as long as the properties that follow in this definition are satisfied, these vectors and scalars can be really anything, right? Any mathematical object. So it's a collection of objects together with scalars and two operations vector addition which is again of course denoted by x bar plus y bar, etc., right? And scalar multiplication. So we're going to define an operation in which we multiply a scalar, a real number, by a vector, cx. Usually we don't write a specific symbol between them, although just by convention, remember, if you don't specify anything, you imply that's a multiplication. There are other types of multiplication involving vectors like cross or dot product. So it's important to separate the two. Usually the context decides what type of operation you're dealing with anyway, right? Sometimes this is called internal operation because it involves vectors themselves. And this is external operation. That's not important, just as a matter of terminology, because it involves essentially taking one element in a different set than the vectors themselves. So you take a scalar, which belongs to real numbers, and another object, which is completely different, right, from the set of vectors, and multiply them together. So you have these operations with a set of properties which are grouped by categories. I don't think I'm going to fit them in this slide. So let's see if let me write down again this, because I'll move on to the next page so I can have all the list of properties in a single slide. So once again, we have a collection of objects with that typical notation together with scalars, which are real numbers for all our purposes, and two operations, vector addition, scalar multiplication, with a set of properties which we're gonna let's write them down on the next page. So I'm gonna stop this slide and we're gonna move on to the next one. Okay, so let's continue with our definition. So we say that a set V is a vector space if the following hold. We have in total actually 10 properties. You'll see that most of the time you don't have to check all of them to make sure that something is a vector space. and they are grouped into categories. So the first category are the so-called closure properties. The first one is that the sum of the two vectors x plus y is in V for every two vectors, or every two elements x, y in V. So that means if you pick two objects and you add them up, now of course that depends on how you define that vector addition, right? So for any two vectors or three elements in V, the sum of them is also in V. Obviously, to understand these properties, you have to run a couple of examples to see actually when it's obvious that it holds, and more importantly, to see when it doesn't hold. Most of the time, this definition is really understood when you look at situations when one of these properties does not hold, because otherwise it doesn't make sense always, you know, what do I mean by x plus y is in V? We have to see an example when it's not, right? The second closure property, the scalar multiplication Cx is in V, again for every x in V and any scalar C, any real number. Those are the closure properties. And then addition properties or additive properties, properties specific to vector addition. There is a zero vector, zero bar, also named additive identity. That means there has to be a vector, sometimes denoted by zero bar, that has the role of additive identity. What does that mean? It means that if you take an A vector and you add to this zero vector, you should end up with the same thing, right? So x plus zero bar equals zero bar plus x equals x for every x in V. Then the next property is the existence of the additive inverse or the opposite of a vector, right? So for every x in V, there is another vector which we can call it minus x in V, such that x plus negative x equals negative x plus x equals 0 bar. Right, these are basically operations that make sense in the context of addition, right? I hope it's pretty clear. So the fifth property, what's also specific to addition? Associativity. You should be able to group however you like additions of a bunch of vectors, right? So x plus y quantity plus z should be equal to x plus quantity y plus z, again for every x, y, z in V, in, excuse me, capital V, right? The set of vectors. And there is also commutativity. The addition should be commutative. X plus y should be equal to y plus x for every x, y in V. And finally, the last set of properties are more specific to scalar multiplication. Properties. What's the count now? 7, right? The 7 property. We need to have an multiplicative identity. which is basically you need to have a 1 in the scalars, such that if you multiply it by a vector, you get the same vector. 1 times x equals x. All right. Notice it, the scalar multiplication doesn't have to be commutative, although most of the, I mean, you're going to deal with real numbers, and obviously, you know, in that case, multiplication is also commutative. We have distributive properties. If you take a scalar and multiply it by a sum of the two vectors, you should be able to distribute that scalar. And furthermore, if you have a sum of two scalars, let's say c plus d, that you multiply by a single vector, you should be able to distribute that vector as well. So c plus d scalar multiple x should be equal to cx plus d, cx plus dx. Right, so these are the distributive properties. And finally, there is an associativity property related to scalar multiplication. This actually appears often in the context of the vectors you will see. You basically can pull out the scalars out of vectors. So let's say you have c quantity dx. That should be equal to, you can group basically cd as a scalar and then scalar multiple with x. So again, these should hold for every x, y in V, and for every scalars C and D. All right, so you should probably write this down and have this information in front of you as I move on to the next page while we go through a couple of examples to illustrate how these properties hold, especially in the case when it doesn't hold, right, when something is not a vector space. So stay tuned for the next page. All right, so I have a remark here about, before we move on to a couple of examples, well, let's actually write down the remark, and then I'm going to make a side note, which is not really strictly important. I usually don't go over it during the live lecture because there is not enough time, but I figure for those of you who are more theoretically inclined might be curious about it, because there are lots of other immediate properties that follow from the definition. Typically, mathematicians want to set up the minimum set of axioms in a definition, and then whatever is additional that can be proven, it's not part of the definition. Although, in addition to what you have listed in the previous slide, there are other important but immediate properties of these operations. So let me write down the remark first, because that's actually important to keep in mind. The closure properties can be checked at once, so both of them, by verifying that cx plus dy is in V for every x, y in V, and every scalar C and D. So in other words, if it's closed under linear combination, right? So you don't have to check those two properties separately. So what follows from now, it's optional, because I can give you a little proof why that's the case. So it boils down to the fact that there are other things that are immediate consequences of the previous operations, right? So we already have in the definition that 1 times x as a vector equals x as a vector, but also if scalars are real numbers, I mean, scalar operations also has additive identity. So let's look at the 0 times x bar. 0 times x bar as a scalar multiplication is also, as you might intuitively expect, 0 bar. Right? That's not part of the definition, although, again, it begs the question, is it true? I mean, just like 1 times x bar equals x bar, which is part of the definition, one scalar multiply x bar is x bar, is it true that 0 as a scalar, not to be confused with the 0 vector, is it true that that gives me the 0 vector? Actually, just a quick example, right? So if you have, for instance, column matrices, right? Clearly, if I do 0 times AB, 0 as a scalar, then you have 0A, 0B, 0 times A, 0 times B, which is 0, 0, which is actually what constitutes the 0 vector, right? If you look at the set of scalar of column matrices. But actually, you can prove that that's the case. That's not part of the definition, right? So what's optional is the actual proof, right? I mean, if you, let me see if I can give you a quick proof, a sketch of proof at least. So we can start with 0 x bar, right? Which we know it's a vector because 0 is a scalar. So we have a scalar multiplication between 0 and a vector. Now 0 is also 0 plus 0. And we also have distributivity, right? And basically 0x has to be equal to 0x plus 0x, which means 0x acts as the additive inverse of 0x, of itself, basically. So it acts as the additive inverse of itself, and without getting too deep into the absolute algebra, there is a uniqueness of the inverse, of the additive inverse. So already we know that 0 bar has that property. So we know that, on the other hand, 0x has to be equal to 0 bar plus 0x. So from these two conclusions, it must be the case that 0x bar has to be the 0 vector. But again, this is optional. I'm just saying that you can assume from this point on that this holds. So what this has to do with the closure properties? Well, we can check both properties, closure properties, before once you know the closure under linear combinations. Because, for example, if C equals D equals 1 and the closure under linear combination holds, then it means that x plus y is in V. And if, let's say I take C to be 1, C to, let's say D to be the 0, and then C arbitrary, then I have Cx plus 0y, which is the 0 vector, which is Cx, and that's also in V. So basically, the key thing, and again, that's mandatory, that's important to remember, the key thing for vector spaces to check the closure properties is to take any linear combination, you pick two vectors, you pick two scalars arbitrary, so if that linear combination is in V, for any two vectors and any two scalars, you basically cover the closure properties. And in practical applications, most of the other properties follow, like I said, from the context. So let's give examples of vector spaces. I already alluded to the column matrix, right? So in all of these examples, I'm going to describe the set itself. So V is all column matrices. I'm gonna with matrix addition and scalar multiplication, right? And I'm going to illustrate it with column matrices of two components so that we don't have to write too much, right? So for example, if you look at checking the closure properties, right? I can take a scalar C in a typical column matrix, and I take a scalar D in another typical column matrix. So two arbitrary vectors and two arbitrary scalar. So following up with the known with the known matrix operations, it's pretty obvious without too much, elaboration and discussion. It's pretty obvious that this is satisfied. What you end up with is another column matrix. Pick two column matrices, pick two scalar. Under the usual matrix operations, you end up with a column matrix, so you're done with the closure properties. And you'll quickly realize that all the other properties in that list, we don't really have to go through that much work to check that they are correct because they are inherited from the already known properties of matrix operations, right? So what's the zero vector? Well, obviously the zero vector is 0, 0, right? If I add 0, 0 to any column matrix, obviously I end up with the same column matrix, X and Y, right? So if it's obvious, we don't check it. The same thing for associativity, the same thing for the additive identity, and so on and so forth. You only basically check what's not obvious, and this depends on the context, like I said. Here's another example. V is the set of all matrices in general, M by N. This is also a vector space, right? So we can illustrate it again for, let's see, for 2 by 2, right? So let's say I'm looking at 2 by 2 matrices. In that case, again, closure property, I'm not going to write it down one more time because it looks the same. What's different? Well, what's the zero vector? That's going to be all the, all matrices with 0 entries, right? So if I add zeros everywhere to a 2 by 2 matrix, I get the same matrix. What is the additive inverse? Well, given a matrix A, B, C, and D, if I take the negative entries and add it to the original matrix, again, using the matrix operations, clearly you end up with 0, 0, 0, 0. So these are obvious examples. Let's move on to the next page to see some slightly less obvious or less known examples. All right, so my third examples. V is all polynomials, and pay attention to these examples, pay attention to all of them, but in particular this one, all polynomials of degree less than or equal to n. The typical notation will be Pn, P with this thickened side here, just to distinguish it from just a variable P. So let's give an let's illustrate the closure again, because that's the essential thing. So the vectors are polynomials themselves. Scalars again are real numbers. So for example, P2 will be made of all polynomials. Let's write them down like a plus bx plus cx squared with a, b, c real numbers. So closure property again clearly holds, right? So let's briefly illustrate, right? So if I take some number, let's call it m, multiplied by a polynomial a1 b1x plus c1x squared plus n a2 plus b2x plus c2x squared, again without too much work, I can clearly see if I come up with the operations. These are operations inherited for real numbers, right? I can group, basically I can factor x squared and combine the constants. So it's not that hard to see that you end up with a polynomial, pay attention here, less than or equal to, of the degree less than or equal to 2. Why is it less than and not equal to? Well, the reason is because under this operation, you cannot guarantee that you preserve the degree, right? So this for example can be 0, can be real number, but any real number can be there, so including 0. So that's why you have to say for this to satisfy the axioms of a vector space, we need to take the polynomials less than or equal to a certain degree. Less than or equal to because it cannot be greater, right? I mean, if I stick to a maximum degree, then any combination, any linear combination is going to be either that degree or lower if the leading coefficient happens to be 0. So that's why if I say, here's the vector v, and I say all polynomials, right? All polynomials of degree exactly equal to 2. right? That's not going to be a vector space because it does not satisfy the closure properties. And whenever you have to show that something is not a vector space, always be prepared to actually provide a counterexample. So for full credit in my exams or the quizzes, if your answer is yes, then check the non-obvious property. To make it easy, actually, I'm going to indicate. I'm not going to ask you to just figure out because, especially if it's a short quiz, I don't want you to spend too much time looking at all those 10 properties, right? But you should be able to recognize which one is not obvious so you can check. But more importantly, because this is where you actually prove that you understand the concept, if the answer you think it's no, immediately show a counterexample. A counterexample that violates one of those properties. Like, for example, closure is not satisfied, which is the case most of the time. Or maybe there is no identity inverse or something like that. So polynomials of degree specific to a specific number, they are not vector spaces, right? What is the counterexample? So for instance, let's say let's call it u bar, right? So one polynomial is minus 1 plus 3x minus 2x squared. Just make sure that under addition, or under linear combination, the leading coefficient cancels, right? And then the other one, v, is, let's say, 5 plus 7x plus 2x squared. So clearly that if I add the two, I get minus 1 plus 5, which is 4. 3x plus 7x is 10x. And then the other one cancels. So this is not of degree 2. So that's not a vector space. All right, so let's see, let's talk about some other examples in the context of, well, actually, let's introduce another important definition, and then we're going to finish up the lesson with other examples. Another very important notion is the notion of a subspace of a vector space. So we say that, let me actually formulate it differently. So suppose V is a vector space then a subset W of V is a subspace of V if W is a vector space itself. Under the same operations of V. In the beginning, when you study vector spaces, again, this definition doesn't seem like much, but it's actually crucially important, really, really important. And why is that the case? So, first of all, because there are large vector spaces, comprehensive vector spaces, but in the particular applications, you're dealing with a subset of those vector spaces, not with all of them. For example, you already noticed in the previous page that I talked about a vector space of column matrices and a vector space of matrices in general. So the idea is that if I actually know already that I'm dealing with vectors in the general sense, like all matrices, but in the particular application I deal only with column matrices, it's important to know that that subset of column matrices also follows the same properties of a vector space. And if that's the case, you don't have to check all of them because most of them are inherited. So let's go back. I mean, I'm not going to go back on my slides here. I'm not going to write all the definitions, but if you look back to those definitions from 1 to 10, you will realize that with the exception of closure, all of the other properties pretty much follow nearly all of them obviously follow from the fact that you are taking elements from an existing vector space. So for that reason, the important theorem related to this is that if closure is satisfied, you're guaranteed to deal with a subset, with a subspace. So let's formulate it as a theorem. So again, suppose that, well, let's just write down the theorem immediately, right? So if Cx bar plus dy bar is in W for every x, y in W and any scalars C and D, then W is a subspace, a vector subspace of V. So you only have to check closure, for example. Let me give you another example besides column matrices, right? Well, actually, yeah, let me think a little bit. Well, let's write it down again here, and I'll move on to the next page to have more space. So the example before, again, we had V, let's say, all matrices, M by N, right? So that's a vector space. Well, that's not a good example. Let me, I was thinking about something, scratch that. I'm not, because I mentioned columns as a subspace of these matrices, so let's scratch that because I had something else in mind. So let's actually move on with, I'm gonna scratch this down and move on to the next slide, and we'll go through for a couple of examples. So stay tuned for the next slide. All right, so let's take a look at a couple of examples where the question is the W a subspace of V? So is it a subspace, V, W of V, subspace of V? So I'm going to specify the vector space. We're going to start with a vector space always. So let's say polynomials of degree less than or equal to 5, right? P5. We know it's a vector space. And I'm going to write W polynomials of degree less than or equal to 2, which again, remember the notation is P2. So is P2 a subspace of P5? So think about for a second, and if you understood all we talked about up until this point, you probably should realize the answer is yes pretty quickly, right? Why is that? Well, first of all, it's a subset, right? Every polynomial of degree 2 by default has a degree less than or equal to 5. So it's clear that W is a subset of V. Is it closed under linear combination? Yes, because if I take any two combinations, C times A1 plus B1x plus C2 C1 x squared, let's call M actually the first scalar, plus N times A2 plus B2x plus C2x squared. Again, I'm not gonna, so we have, well, let's write it down one more time. MA1 plus NA2 plus MB1 plus NB2x plus MC1 plus NC2x squared, right? I mean, we already know actually P2 is a vector space on its own. So the answer is yes, right? I mean, whatever you do, whatever linear combination you come up with in with elements with the polynomials degree less than or equal to 2, obviously you end up with the polynomial of degree less than or equal to 2. So it's a subspace of P5. So that's pretty obvious, maybe even too trivial. Here's a one that is not as trivial, right? So let's say V is given by all matrices 3 by 3, and W is so-called all upper triangular matrices 3 by 3. Upper triangular means zeros over the main diagonal. Okay, so a typical example of a matrix in this case will be, let's see, let's write it by column: x1, y1, z1, then 0, x2, let me see if I have a nicer notation. Let's say y2 here, y2, z2, some notation that makes more sense, right? 0, 0, z3. You know what? Let me actually use a different notation. Sorry, I didn't think of this through yet. So let's say, okay, let's say I'm not happy with the notation, so I'm gonna use, because I don't want to overcomplicate it. Let me think a little bit. Trying to figure out what's the best notation. x1, x2, x3. You know what? Let me. Yeah, let's count these. Let's use the single letter, and let's just count them by column, right? So let's say you have x1, x2, x3, 0, x4, x5, 0, 0, x6. That's not ideal, but I think it's better. So the idea is that you have all entries arbitrary except the top. On the top, I mean, except the elements on over the main diagonal, which should be all zeros. And then let's take another one, and I'm going to use y. Let's say you have y1, 0, 0. That's y2, y3, y4, y5, 0, y6. Okay, so the question is these types of matrix closed under linear combination? Right? If I take, for example, a linear combination, so let's say a scalar times the first matrix plus another scalar times the second matrix, will I end up with the same type of matrix with 0 on the main diagonal? So I'm not going to write all the elements here because it's kind of too tedious. Maybe the first one, right? So the first entry will be mx1 plus n y1, but then the other ones will be 0, right? Okay, so n times 0 plus n times 0 is 0. So I hope it's pretty obvious that while the main diagonal might not be 0, the upper elements, the elements on top of the main diagonal will still be 0. So this is closed under the linear combinations, right? So the element here on the last corner will be what? M x6 plus n y6. And all of these guys will be maybe not equal to 0, but the elements on the top of the main diagonal are all 0. Sometimes these properties to check are kind of tedious. I should have, I mean, if you take, for example, the 2x2 version, it's kind of trivial because you have only 1 0 on the top. Let's actually look at some other examples. Let's say not involving matrices. So, well, actually, let's do another one that involves matrices. So let's say V, again, is as overarching vector space is given by all column matrices. And W, let's say it's all column matrices with positive entries. That's an example in which it's not going to be a vector space. Why? Because it's not going to have an additive identity, right? Like, for example, let's say you have, or it's not closed, right, under the linear combination, because you can end up with a combination that gives you negative entries. So for example, let's pick 2 elements in W, right? I'm going to pick, let's say, and let's actually use actual numbers. So let's say 2, 5, and another element, let's say 1, and I don't know, let's say 1 and 2. Well, if I look at the linear combination using, let's say, the scalar 1, plus the scalar minus 7, then the resulting matrix will be 2 minus 7, which is negative 5, 5 minus 14, 5 minus 14, which is negative 9. All right, so obviously this is not in W the way I define it. So basically not a subspace. Let's take a look at other example. Let's actually take a look at examples in which vectors are functions, because for example, let's look at V defined by all continuous functions. And W given by, say, functions such that, real functions, right? Such that, let's say, f of 0 equals 3. Right, so first of all, is W a vector space? So V is a vector space. Again, in this case, all the properties are inherited from real numbers, right? I mean, you multiply a number by a function, and the key thing is that if I have two continuous functions, if you take, for example, a linear combination, a f of x plus b g of x is actually continuous. So the original V is a vector space, right? Again, I'm not going to go over all the details, but what's the key thing to check, right, to see if it's a vector space? The question is this linear combination also continuous? But remember, the definition from calculus says that a function is continuous if you take the limit, then the limit is defined, it exists, and it's equal to the function evaluated at the limit point. So when you take a linear combination involving two continuous functions, it's just a matter of passing the limit. So you know you can pass the limit in a summation like this, and you're guaranteed that each term has a limit because they're continuous, so therefore this is continuous under this operation. So in other words, this property holds because you know from calculus that summation of continuous functions is itself continuous, right? Or linear combinations of continuous function is continuous. What about the subspace itself? Well, again, this might not be obvious, but the answer is, at least in the beginning, although with some experience, the answer should be obvious pretty quickly, right? That the answer is actually no, right? So W is not a subspace. So again, most of the time, the counterexample comes from the violation of the closure property. So if you take, for example, fx, let's take two simple examples in which f of x is equal to f of 0 equals 3. That easiest thing is to take, polynomial function. So let's say f of x equals 3, equals x plus 3, and g of x equals, let's say, minus x squared plus 2x plus 3. Right? In both cases, f of 0 is 3, and then g of 0 is 3. And yet, if I take the sum of the two, which is actually minus x squared plus 3x plus 6, clearly, if I evaluate at 0, f of 0 plus g of 0 is not going to be equal to 3. That's a key thing to understand, especially in the context of differential equations, which is my next and probably my last example. That's going to be important part related to the solutions of linear equations that you're going to learn in the context of differential equations. So if you impose a specific value for a function, especially at 0, it's very easy to understand that that will not result in a subspace. So stay tuned for probably the last slide. All right, so those of you who take my class will also take or are taking the differential equation class. So I'm not going to get ahead of myself too much, or ahead of your instructor, but you will discuss in more depth in that class with basically something that has the structure of a vector space, again, in the context of that class. So I'm going to illustrate it here, but again, you will go over this concept in more details. But I think it's just important to establish the main idea in the context of the linear algebra component of the course. So you will learn in that class that a differential equation has infinitely many solutions. And you learn that under some conditions this form a vector space. That's the central theme in the context of linear equations. So you will learn that homogeneous linear equations, linear differential equations, form a vector space. Homogeneous linear equations, as an example, they have the structure of, let's illustrate it with a 2 by 2 case, with an order 2 case. Some function of t, y double prime, plus some other function of t, y prime, plus some other function of t, y equals 0. So some linear combinations involving functions of the independent variable t and the derivatives of the dependent variable and its derivative, right? So linear combinations of y, y prime, y double prime. But non-homogeneous, so as long as you have 0 on the right hand side, so if there is no isolated term that depends on t alone, and non-homogeneous linear ODEs do not form a vector space. So those are equations in which, again, the right hand side might depend on t explicitly, say some function f of t on the right. So let's establish why that's the case. So suppose, and let's actually do an example in which the coefficients are constants, because I can illustrate with an example in a minute. All right, so let's say you have, for instance, y double prime plus 4y equals 0, right? I can give you the two solutions in a moment. I mean, you're going to learn how to solve this, or probably you learned this already. I think you learned this already, that y1, yeah, you know what, let me just illustrate it differently. So suppose y1 and y2 are two distinct or independent solutions. All right, and we look at as the candidate for the vector space V, we look at all solutions of this particular ordinary differential equation. All right, so let's check, how do we check that this is basically a vector space? At least the closure part, okay? So let's think of it as under the overarching vector space of continuous functions, right? Because as it happens here, actually these solutions are continuous as well. But let's look at the closure in particular. So suppose y1 and y2 are in V, right? So again, this is the set where for all the solutions of this particular differential equation. So if I pick two solutions, y1 and y2 in V, that means they satisfy that particular equation. Yeah, so if I plug in y1, I get y1 double prime plus 4y1 equals 0. And if I plug in y2, I get the same. All right, what happens if I plug in a linear combination? So let's check the closure property. So I take some constant, ay1, of t plus by2 of t. Now remember, sometimes we don't write of t because just for convenience, right? We understand that y1 and y2 depend on t. So let's plug it in into the very same differential equation. And again, linearity allows you to distribute the derivative. So a y1 double prime plus by2 double prime plus, and then distributivity on the right, 4a y1 plus 4b y2. And now we can group the terms by y1 and y2 and factor a. And this is the key thing that I'm sure we're going to talk about in more details in differential equations. Linearity allows you to group the terms like this, because originally you picked y1 and y2 to be the very solutions individually for the same ODE. Each parenthesis is 0, right? Because they satisfy independently, each of them, the same equation. So this linear combination boils down to the combination a times 0 plus b times 0, which is of course 0. But the key thing is that this can only happen if you have 0 on the right-hand side. Any other number on the right-hand side besides 0 will violate the closure property. Meaning that the solutions of, in general, a linear ODE, which is not homogeneous, will not form a vector space. So as an example, let's say V instead is all solutions of let's say this y double prime plus 4y equals 6. Let's say equals, let's make it easier, let's say equals 8. And by the way, if you're curious, because again, I think you learned this already, for this particular ODE, two independent solutions that can be found are sine of 2t, cosine of 2t. Right, it's, you study the characteristic equation. Again, I'm gonna get into that, right? If you plug in sine of 2t and cosine of 2t, you're gonna end up with two solutions. And again, if you're curious, in this particular, well, let's not get into that, because again, it's not my job to teach you differential equations. Actually, let's stick to the linear algebra aspect of it. Why? So let's illustrate why this doesn't form a vector space, right? So let's say again that we pick y1 and y2 in V, right? That means, again, individually, y1 and y2 does satisfy the same ODE. So y1 double prime plus 4y1 equals 8, y2 double prime plus 4y2 equals 8. Actually, maybe it's a good idea to provide a full solution. So again, in the previous case, the full solution is just any linear combination of that sine of cosine of 2t. Whereas here, and again, this is, you're going to learn this in the your ODE class, a full solution or the general solution of this equation is c1 sine of 2t, c2 cosine of 2t plus 2. You're going to learn something related to the, particular solution and so on and so forth. All right, so let's pick two solutions in this equation. So each solution is obtained by some values of those constants, c1 and c2, right, which are arbitrary constants. And let's look at a linear combination just like before. So if I check whether a linear combination ay1 plus by2 is a solution of the same ODE for quantity ay1 plus by2, you can do the distributivity just like before. So we can pass the derivative to each term. We can do again the rearrangement of the terms just like before. But now, because each of them satisfies the same ODE, you're gonna end up with a times 8 plus b times 8, and of course this is not going to be equal to 8 for every a and b, so it's not going to solve the same equation. It's not going to be from the same space, right? I mean, for example, let's say a is 1, b is 1, right? That's not going to be true. A plus 8 is not going to be obviously equal to 8. So I hope it's clear. That's one of the essential things to understand the difference between homogeneous and non-homogeneous linear ODEs. The structure of a vector space is given in the context of, occurs in the context of linear and homogeneous differential equations. So I think that's it for today. We'll do things in a slightly different order. My next topic is to show you how to find eigenvalues for 2x2 matrices, because you're going to need this sooner in your differential equation class. And then we're going to move on with linear transformations, and then we'll go back to the concept of eigenvalues and eigenspaces in a more detailed way. So that's it for today.